Hi, this is S. Lakshmanachari, working as an assistant professor in Department of Cyber Security, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss problem solving on asynchronous data transfer. So this asynchronous data transfer, it is used in a data transmission. So data transmission means data transmission is the process of transferring information from one place to the another place, or transferring the information from sender to the receiver. That is called data transfer. So this data transfer, it takes place in two ways. One is the serial data transmission, and another one is a parallel data transmission. So data transmission, it will take place in two ways. One is the serial data transmission, and another one is the parallel data transmission. So serial data transmission means transferring of information bit by bit. That is called serial data transmission. On the other hand, parallel data transmission means transferring the data byte by byte. That means a group of 8 bits we are sending as bytes from the transmitter to the receiver. So that is called parallel data transmission. So on again the serial data transmission, again they are classified into two types. First one is a synchronous data transmission, and another one is a asynchronous data transmission. So we are discussing about asynchronous data transmission. So the internal operations in a digital system are synchronized by means of clock pulses supplied by common pulse generator. So most of the internal operations of any digital system, they are synchronized by means of some clock pulses, and these clock pulses are generated by using the common pulse generator. So the pulse generator, it will generate various types of the clock pulses, like different types of clock pulses are there: square, rectangular, triangular. So like that, in general, the clock pulse, as a clock, we are considering the square pulse, square wave. So if the registers in the interface share a common clock with the CPU registers, the transfer between two units is said to be synchronous data transfer. Already we have seen two types of the serial data transmission. First one is a synchronous data transmission, and the second one is a asynchronous data transmission. So synchronous means the interface share a common clock with the CPU registers. Then that is a synchronous data transmission. In most cases, the internal timing in each unit is independent from the other, in that each uses its own private clock for internal registers. In that case, two units said to be asynchronous. That means if the two units they uses a separate clock pulse, then that is said to be asynchronous data transfer. That means suppose if you are transferring the information from source to the destination. So if the source and destination they uses their own clock pulse, then that is said to be a asynchronous data transfer. So asynchronous data transfer between two independent units requires that control signals be transmitted between communicating units to indicate the time at which the data is being transmitted. Okay, so in asynchronous transmission, between the two units, we are using some control signals. Okay, so that indicate the time at which the data is being transmitted. That means, suppose if the sender is transmitting the data to the receiver, okay, sender or source transmitted the data to the destination unit. So when the destination unit, it doesn't know when the source unit transfers the data. So in order to facilitate the communication between the source unit and the destination unit, we are providing some control signals in the asynchronous data transfer. So in a communication system, in a computer system, CPU and I/O interfaces are designed independently of each other, because in a computer system, the CPU and the I/O interface, because the computer mainly it consists of three components. One is a CPU, and another one is a I/O subsystem, and the third one is a memory subsystem. So out of these three, this CPU and I/O interface, they develop independently. Okay. So when the internal timing in each unit is independent from other, and the registers in interface and the registers of CPU, if they uses a separate clock for the interface and the registers of CPU, then that is said to be asynchronous data transfer. And this asynchronous data transfer, it takes place in two ways. First one is using strobe control or strobe pulse, and second one is handshaking method. So using these two techniques, we can facilitate this asynchronous data transfer. First one is strobe pulse. So using the strobe pulse, how we can initiate a asynchronous data transfer. So this strobe pulse is a control signal. So by using this control signal, we can communicate the source unit with the destination unit. And this control signal, it is supplied by one unit to indicate the other unit when the transfer has to occur. So the strobe may be activated by either source or the destination units. So first one is a source initiated data transfer, and second one is a destination initiated data transfer. So let's see one by one how the data will be initiated by using this strobe pulse. So this is a source initiated data transfer. So you can see here the block diagram of the source initiated data transfer. So this is a source unit and this is a destination unit. So the source unit and the destination unit, they are communicating by means of two control signals. One is the data bus and another one is a strobe pulse. So data bus, which carries the data to be transmitted. That means we are transferring some information from the source unit to the destination unit. So whatever the information to be transmitted, that passing through this data bus. Okay. So once the source unit, it places a valid data in the data bus, the source unit will initiate a strobe pulse. So this strobe pulse, we are applying to the destination unit. So once the destination unit, it receives this strobe pulse, it can come to know that a valid data is placed in the data bus, so that the destination unit will read the data from the data bus. So in this way, the source will initiate the data transfer. So the same thing we can represent using the timing diagram. Okay, so this is a source and this is a strobe signal. So initially, the source unit will place the data in the data bus. So here, so this is the time at which the source unit will place the data in the data bus. After certain time, the source unit will initiate the strobe pulse. So this strobe pulse will be received by the destination unit, and the destination unit come to know that a valid data is placed in the okay. So valid data is placed in the data bus, so that the destination unit, it will read the data from the data bus. So in this way, the source will initiate the data transfer. And coming to the second one, that is destination initiated data transfer. So here you can see the block diagram. Okay, so source unit and this is a destination unit. So the destination unit, first it will send an strobe pulse to the source unit. Whenever the source unit, it receives the strobe pulse, then only the source unit will place a data in the data bus. Then after placing the data in the data bus, the data will be read by the destination unit. So the same here you can see. So first the store pulse will be generated. After certain time, the data will be placed in the data bus, and then the data will be read by the destination unit. So that is a destination initiated data transfer. So, but here in this store pulse, we have some drawback because the destination similarly, the destination initiates the transfer. It has no way of knowing whether the source unit has placed the data on the bus or not. So this data destination unit, it doesn't know whether the source unit has placed the data in the data bus or not. Okay, so this is a drawback in the strobe pulse. So to overcome this drawback, we are going for the second method, that is called handshaking. Handshaking method. So using this handshaking method, we can overcome that problem. Okay, so in the handshaking, the receiving unit responds with another control signal to acknowledge the receipt of the data. So that means here the handshaking method, it solves the problem raised in the stop method by introducing a second control signal. That second control signal is the acknowledgement. Acknowledgement. So that means this is source unit, this is a destination unit. So suppose if the source unit sends the data to the destination unit. So here the source unit, it doesn't know whether the destination unit is received that transmitted data or not. Similarly, when the source unit sends the data to the destination unit, the destination unit, it doesn't know whether the source unit placed the data in the data bus or not. So in order to overcome that, we are introducing one control signal, that is acknowledgement. Again, here also in the handshaking method, two types are there: source initiated and the destination initiated. Here in the source initiated transfer using handshaking, so two control signals are there. One is the data valid and the second one is the data accept in addition to the data bus. So this is source unit, destination unit. So initially the source unit will place a data in the data bus, and after that the source unit will send a data valid signal to the receiver or destination unit. Okay. So once the data unit it receives the data destination unit will send a data accepted signal to the source unit. So once the source unit it receives the data accepted signal, it can come to know that the transmitted data has been received by the destination unit. So this is a source initiated transfer using handshaking. So the same thing we have represented in the timing diagram. So this is a first the data will be placed in the data bus. After that, the source unit will initiate the data valid signal, and after that, the source unit will receive the data accepted. And similarly, the second type, that is a destination initiated transfer using handshaking. So here also we are using two control signals. One is data valid and ready for data. Here you can see the block diagram. One is the source unit and the second one is the destination unit. So first the destination unit will send an ready for data signal to the source unit. So first it will send the ready for data. That means the destination unit is ready to receive the data from the source unit. Once the source unit it receives this ready for data, then the source unit will place a data in the data bus. Then the source unit will initiate the data valid signal. So that whenever the destination unit receives the data valid signal, then the data it will read the data from the data bus. Okay, so this is a second type of the handshaking. So coming to the problem solving, So the first question is, how many characters per second can be transmitted over a 4800 baud line in each of the following modes? Assume character code of 8 bits. So here we are transferring the data using asynchronous data transfer, and the baud rate is 4800 baud line or baud rate. That means baud rate means the number of characters transmitted per second. That is the baud rate. That means per second 4800 bits we are transmitting, and we are assuming the character code of 8 bits. That means each character code length is 8 bits. So we need to find the number of characters transmitted per second in synchronous serial transmission. Similarly, asynchronous serial transmission with 2 stop bits. Similarly, asynchronous serial transmission with 1 stop bit. Because in asynchronous transmission, we are using this start bit and stop bits. But in the synchronous serial transmission, we don't use any start and stop bits. Okay, so that is so see the solution. So first one, synchronous serial transmission. That means the number of bits we are transmitting per second using synchronous serial transmission. So in synchronous serial transmission, we are not using any start and stop bits. Only the number of bits we are transmitting from the source unit to the destination unit. So the number of characters transmitted per second, that is equal to, the formula is baud rate by the character length. So already the baud rate is given in the problem, 4800. 4800. So in synchronous serial transmission, the character code length is 8 bits. So 4800 by 8. Okay, 8 6 48. So 600. That means using synchronous data transmission technique, we can uh, we can transfer the number of characters per second is 600. So that means using synchronous serial transmission, 600 characters can be transmitted per second. And coming to the second one, that is asynchronous serial transmission with 2 stop bits. With 2 stop bits. That means in asynchronous serial transmission, we are transferring the data using start and stop bits. Suppose if this is a data to be transmitted, so here we are using 1 start bit. Here we are using 1 stop bit or 2 stop bits. So this is how we are transferring the data from the source unit to the destination unit. But here, as for this, we need to find the number of characters transmitted per second in asynchronous serial transmission with 2 stop bits. With 2 stop bits. So number of characters transmitted per second is equal to baud rate by frame length. Because along with the data, we are transferring the start bit and stop bits also. So that's why the baud rate by frame length is equal to 1 start bit plus 8 bit character code and 2 stop bits. So just before we have seen, so this is 1 start bit and 2 stop bits, 1 start bit and 8 bit length. So total the frame length is 2 plus 8 10 plus 1 11. So see here, this is 1 8 2 9 plus 2 11. So that means the length of the frame is 11. So 4800 by 11, that is equal to 436.36. So if you round it, you will get 436. So that means 436 characters can be transmitted per second using asynchronous serial transmission with the 2 stop bits. The third one is asynchronous serial transmission with 1 stop bit. 1 stop bit. That means here we are sending 8 bit data, 1 start bit and 1 stop bit. So one stop bit, 8-bit length. So total number of bits equal to 10. So that is equal to baud rate by one start bit, 8-bit character length, and one stop bit. So total 10. So 4800 baud rate by frame length 10. So you will get 480. That means in asynchronous serial transmission with one stop bit, we can transfer 480 characters per second. So in this way, we can find the number of characters transmitted per second using in both synchronous and asynchronous data transfer. Coming to the second question, how many bits are there in the transmitter shift register of below figure? When the interface is attached to the terminal that needs one stop bit. List the bits in shift register when the letter W is transmitted using ASCII with even parity. So here they have given us asynchronous transmission interface circuit. So this is a asynchronous data transmission interface. So this is a transmitter section, and this is a receiver section. Okay, so the data here we have a shift register. Here we have shift registers. Okay, so we need to find the number of bits in the shift register when the letter W is transmitted using ASCII with the even parity. Okay. So this is a list of ASCII codes. So ASCII full form is a American Standard Code for Information Interchange. So it is every character we are representing using 7 bits. So it is ASCII is a 7-bit code. That means 7 bits are used to represent each character in the ASCII. Okay, so suppose if at the rate is there. So if at the rate we are representing using this one. Okay, using 0000 001. So if you write B1, B2, B3, B4, B5, B6, B7. So total 7 bits are there. Bit 1, bit 2, bit 3, bit 4, bit 5, 6, 7. So that means the order from B1 to B7. So 0000001. So that is a ASCII code for the at the rate. Similarly for capital A, capital B. So these are all the various ASCII codes for different letters and special symbols. So as stated in the problem statement, we are transmitting W letter, W from source to the destination using ASCII. So the number of bits in the transmitter shift register are 10 bits. So the number of bits in the transmitter shift registers are 10 bits. So 10 bits is equal to 1 start bit and 1 7-bit ASCII code and parity bit and stop bit. So this is 1 start bit, 7 bits, parity bit, this one 7, 8, 9, 10. So total that is equal to 10 bits. Okay. So from the table ASCII equivalent of W is 1010111. So here you can see B1. Okay. So 1110 101. Okay, so we have written, see here. So we have written B7, B6, B5, B4, B3, B2, B1. So in this way we have written. So 1010111. Okay. So this is a actual 7-bit data we are transferring from source unit to the destination. With the even parity. With the even parity means in the given ASCII code, the number of ones are 1, 2, 3, 4, 5. That means it is having odd parity. But to make it even parity, we need to add one more 1. One more 1. So the parity bit 1 is added here so that it becomes even parity. Because in even parity, the number of ones in the transmitted data is always even. So this is 1, 2, 3, 4, 5, 6. So now it becomes a even parity. And then we are adding one start bit and stop bits. Okay, so with start and stop bits, so start bit, so always the start bit is equal to 0 and stop bit will be always 1. So if you append start and stop bits, so this is a start bit and this is a stop bit. So this is stop bit, this is even parity, and this is a ASCII value, and this is start. So finally, this entire data we are transferring from source unit to the destination unit. So the slides are prepared by referring the textbook M. Morrismano, Computer Systems Architecture, Pearson, 3rd edition, 2015, and also referred John D. Carpinelli, Computer Systems Organization and Architecture, Pearson, 1st edition, 2001. So in this lecture, we have seen the introduction to the asynchronous data transfer, and also we have solved some problems related to the asynchronous data transfer. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.